Hello, my name is JCATI, and this is my carbon fiber recycler project sponsored by JCATI. This project is in its fourth year of progress at Central Washington University. The goal of this project is to delaminate, shred, and pyrolyze carbon fiber composite strips produced from Boeing 737 aircraft trimmings. My focus of the project was to increase the rigidity of the crushing housing. As you can see, there's not a lot of support underneath the previous assembly, allowing for misalignment in the gears driving the crushing wheels. I chose to implement a base plate fixture that would increase the rigidity of the crushing housing and hopefully provide a more thorough delamination process. Now the main requirement for this project was that the deflection of the gears could not exceed more than 5/1000ths of an inch. The plate needs to hold the crushing wheels with an output speed of 2.5 RPM. The plate needs to withstand the crushing load of 10,500 pounds produced from the delamination, and the feed rate needs to operate at 1 foot per minute. Now, the first and second analyses that were conducted determined the need for the baseplate design. These analyses took deflections of the crushing housing and both of the gearboxes. It was found that they were all moving independently from one another, and the crushing housing was moving downwards with a deflection of 25/1000ths of an inch. So the plate would fix that issue and really just hold all the components together. A flat plate analysis was conducted with the required maximum deflection value of 5/1000ths of an inch. The load used in this analysis equation was found from the equation for a cantilevered beam produced from the deflection of 25/1000ths of an inch found previously, and this produced the load experienced was 467 pounds. After using these two values, it was found that the design of the plate would be made of ASTM A36 steel to a thickness of 3/4 of an inch. Finite element analysis was conducted using Nastran, comparing to the maximum displacement of the green sheet calculation of 4/1000ths of an inch. Nastran produced 3/1000ths of an inch for maximum deflection with an 8.7% error, and this gave us the green light to go ahead with the base plate design as is, and the safety factor of the plate was 1.4. This also allowed for the truss design to be discarded from the base plate fixture. The plate would absorb most of the load and be fine, which is why these analyses were conducted for the truss. The final analysis, we conducted a finite element analysis of the side plate of the crushing housing on the input. The crushing load was applied to each of the mounting locations for the bearings on the top and bottom shafts, and it was found that the maximum deflection was 1/1000th of an inch, and this predicted value would be used for the further testing. The first part of the construction process was deconstructing. We had to disassemble all of the previous assembly and remove the angle iron from the table. This was done using an angle grinder and a bandsaw. It was removed to allow for the flat plate to sit flushly on the supporting table and accurately place all of the components. Some existing parts needed to be modified, including the spacers for gearbox 1. They needed to be milled to a height of 3.79 inches to bring the output shaft of gearbox 1 concentric with the input shaft of gearbox 2. And pinholes were also drilled into the spacers to allow for accurate location. The supporting table was modified with mounting holes once the plate was manufactured. And some misalignment issues were found in gearbox 2, which required the need to cut out the holes for the bolt clearance to fasten gearbox 2 to the table and have those input and output shafts, as mentioned earlier, concentric with one another. The base plate was manufactured on the knee mill using a 3-man team. Multiple configurations were used with a hydraulic lift and C-clamps just to ensure proper level drilling and locating. Now there were multiple configurations because it was a difficult plate to manufacture. The size was an issue, so it took a good chunk of time out of the project. Here's an example of milling the rectangular slot for the chain access from motor 1 to gearbox 1. We placed not housing spacers, but we placed spacers underneath the plate, and this allowed for us to mill through the plate and not have the bit run into the table. The final part that needed to be manufactured were the housing spacers, and these were just to allow clearance for the crushing wheels and the spur gears to operate without running into the base plate. 3 tests were conducted, 2 of them manual, 1 a motor test. The testing locations are mapped out in this diagram. So the testing location underneath the housing, we have the back sidewall and the front sidewall of the input sidewall crushing housing on the upper and lower shafts. The testing device used was a dial indicator and some examples of testing locations. Here's a demo of the first manual test done, and I'll let that run through.
And as you can see, we're running all of the components so that the crushing wheels will run the carbon composite through in turn delaminating it. Now this clip demonstrates test 1, and as the dial indicator you can see is placed underneath the crushing housing, as we run the partially delaminated strip through the crushing wheels, we'll get a deflection value. One of the project members will read that value as I operate it manually and run the carbon fiber strip through the crushing wheels. The test sheet is broken up into four.
Okay, so as you can see, we have 3 testing tables. The first 2 were the manual tests with partially delaminated and full composite. The full composite is to a 1/2 inch thickness, partially delaminated to a 1/4 inch thickness. This table produced the most accurate results. We were able to see that the base plate did its job in preventing downward deflection of more than 5/1000ths of an inch, and it was actually to the predicted value. So that was a success. However, the sidewall deflection was way over the predicted value and way over the maximum requirement of 5/1000ths of an inch. So sadly, we were not successful there. The motor test also was fairly unsuccessful because we were not able to delaminate the full 1/2 inch thick composite. We had to use the 1/4 inch thick composite, and the motor RPM was at 189 RPM, which had the wheels operate at output RPM of 2, which is also unsuccessful. Sadly, we couldn't test the full composite because we were in fear of breaking the components of the system. So some reinforcing of the sidewalls and the shafts and bearings will need to be done next year. The budget for the project is as follows. JCATI provided each project member with $1,250, and luckily there were no labor costs, so we were able to keep the project within 50% of the budget. This is from the appendix in the report of all the parts and cost lists. The schedule, the Gantt chart, tracks progress of the project through fall, winter, and spring quarters. Total amount of time spent on the project was 188 hours. Yeah. If you have any questions, please feel free to leave your email or email me at tommyandj@cwu.edu. Thank you for your time.